Hello and welcome. In this video, we're going to take a look at really a more precise definition of what a limit actually is. We've sort of expressed what a limit is in words and by illustration, but now we can get a much more mathematically precise way to define this limit. And this kind of definition is a little bit more technical, but this also kind of leads you into upper level mathematics where the technical definitions of these concepts are far more important so that we can do analysis on other concepts that arise in higher level mathematics. So it's a good opportunity to see a more formal definition. But first, I'm going to just make sure that we're all on the same page when it comes to how to kind of visualize and how to conceptualize absolute values. So absolute value can be really thought of as a distance. If you're taking the absolute value of x minus a, you know it's always going to be positive. And you can actually represent that as the distance between x and a. So here's an x-axis, and a is a point on there. If x is to the right or to the left of a, then just subtracting x minus a and then taking the absolute value will reduce to a positive value, and this will give you just the distance. How far away are we? It doesn't matter with the direction. And similarly, if we say x minus a has an absolute value less than, and this looks like a d, but this is delta, it's a Greek letter. If that's the case and you have this distance being less than delta, this means that the distance between x and a is less than some cutoff. That means you can travel to the right as far as a plus delta, but not quite including it. So I've got a round bracket. And we can also travel to the left and travel the same distance to the left. And that distance would not exceed a minus delta if you're taking if you're looking at the x values there. So x could be any value in this open interval, and then we know that the distance between x and a would be less than delta. And that would satisfy this equation, or this inequality, absolute value x minus a less than delta. Okay, now keep that in mind. Essentially, we're using that as not just a difference, but as like a distance. So it's always going to be positive. And now we can dive into this technical definition of what a limit is. Now, we mentioned this already the first time we defined a limit, that f needs to be a function that's defined for values around a. So to make that a little bit more precise, let's say it's defined on some open interval that contains a except possibly at a itself. And then let's say that the limit of f of x as x approaches a is equal to some number L. Then for every number, and then we've got the Greek letter here, this is epsilon. Say hello to epsilon. There is a number, delta, which we just saw here in my absolute value definition, such that if the distance between x and a is somewhere between 0 and delta, then the distance between the function and the value L is less than epsilon. Okay, well, if you remember, in terms of just putting this into words, we can say that f of x can be made as close to L as desired, and that is this part right here. When we say we can make it as close to L as desired, we're just saying that the distance can be made less than epsilon. Epsilon is now going to be that as close as we want distance. And the other part of our verbal definition, we can make it as close to L as desired by choosing x values sufficiently close to a. And that's this other part here, that the distance between x and a is any value between 0 and delta. And then to be a little more precise, instead of saying sufficiently close to a, that just means that the distance between x and a is less than delta. And of course, that distance is always going to be positive. All right, well, because now we're talking about distances, we're talking about, well, distances vertically along the y-axis, and we're talking about distances horizontally. Maybe it's good to draw a picture here. And here I've got a function y equals f of x. And just by looking at the graph, you can see that the limit as x approaches a is equal to L. We can take a ruler here and we can draw a little dashed line. And we can see, sure enough, it seems to be able to be as close to L as we wish by choosing values of x sufficiently close to a. Now, what about the epsilon and delta components here? All right, well, how close do we want our function to be to L? Pick a number, and that is our epsilon. Remember, when we say as close to L as desired, that means that the distance from L, above or below, was going to have to be within some sort of margin of error. That's our epsilon. You can think of it like error. We can take a small bit above L or a small bit above L, and we can make it sufficiently close to L that way. And it's time to take the ruler out here and kind of take a look so that we can see when we put that through our function, there's going to be a range of x values that put us sufficiently close to L. Now, time to think about the x values. Is there sort of a range of values of x? Values of x that are within a certain distance of a, so that we're guaranteed that the graph is between those two red lines. Well, take a moment and take a look at this point right here. If I go any further away from a, then my graph is not going to have a y value, f of x, in the red dotted lines. So I won't go any farther than that. I'm going to call that my maximum distance. I can't go any farther than that. That distance, I'll call delta. And this would be a plus that distance, delta. And then if I go out to the other side by that same distance, this would be a minus delta. And I'm going to use my ruler here again. And I'm going to take a look at where the graph is at that distance. And that puts me at this point here. And I could actually travel a little bit further to the left and still be within the red dotted lines. But I couldn't travel any further than that distance to the right and still be in the red dotted lines. So this would be how close I would need to be to A in order to be this desired distance from L. If that makes some amount of sense here, I've got this little distance. And for any values of x in here, so for any values x that satisfy this equation, this inequality, that the distance between x and a is between 0 and delta, so long as I pick any x's in that interval, you can see that the y values are going to fall within the desired distance of L. And so we can definitely say that so long as we only pick values in this, let's maybe shade this in. So long as we only pick values of the function that are in the shaded area, you can see that f of x is definitely somewhere in between L plus epsilon and L minus epsilon. Therefore, the distance between f of x and L is less than epsilon. And now the important part here, this is kind of the most important part to realize, is that this process should be allowed to be repeated for any choice of epsilon. So now if you wanted to, you could shrink epsilon to be a smaller value, and along the y-axis now, you need to be even closer to L. And if you want to be closer to L, we should be able to repeat the process and find another little interval along the x-axis, another little blue shaded area, and that's going to get skinnier so that f of x is still between L minus epsilon and L plus epsilon, and the distance is still sufficiently close. And the closer you want it to be, then you're going to find out that this blue shaded interval keeps shrinking. But we can always find some sort of interval on either side of A that as long as x is in there, you're going to be within your desired margin of error of L. Now, of course, this is, again, just a technical definition for it, and I hope that that at least allows you a glimpse into what a proper definition of a limit looks really like. And this idea, epsilon and delta, we use these two Greek letters kind of by tradition. You'll always see it using epsilons and deltas. And you can think as epsilon is like an error, how we're never going to be quite equal to L. You can see in that example, I actually had an open dot, and I can't actually have the function equal to L. I can get as close as I want. So think about epsilon like the error. You're a little bit above or a little bit below. It's your tolerances. And then delta is kind of the distance horizontally. If I want to be within this little tolerance, I have a very narrow distance on either side of A that will guarantee that my Y value is within the tolerances of L. Well, again, I hope that helps you at least see a technical definition. I don't expect that we'll be using the formal definition very often. And spoiler alert, a lot of these limits are actually going to take a little bit of a sidestep once we learn how to use those to find derivatives in calculus. So, thanks for watching. I'll see you in the next video.